Okay, so looking at this picture, you have your three classes of levers. Okay, you have your first class lever, which is right here. Okay, so notice the relationship of the force arm, the resistance arm, and the axis. So if in a first class lever, the axis falls between the force arm and the resisted arm. Okay, so that the lever that we saw on the previous the previous slide, and that's in your textbook, that is also a first class lever because the fulcrum or the axis, okay, sorry if I use two different terms, but they both mean the same thing. The fulcrum of the axis is between the force arm and the resistance arm. That means that that's a first class lever. Then you have your second class lever. Okay, if we come down here, here's a second class lever. Now what happens is you have your axis or your fulcrum on the end. The resisted arm is in the middle and the force is at the end. So when you're looking at the length, so if you were to measure the resistance arm and the force arm, again, you have to go back to your definitions. Remember, they're the perpendicular distance away from the axis. So if you were to measure your resisted arm, you would measure from here to here. That's the perpendicular distance. Here's your resistance, okay? You measure from there to there. If you're looking at the force arm, you would measure from here to here, okay? So the definition still stays the same. You're just measuring from the axis to the point of your resistance arm and your force arm. Then you have your third class lever, okay? So your third class lever, now you have, so you still have the axis or the fulcrum on the end. You have your force arm, which is right here. Again, perpendicular distance. Okay, so there's your axis to your force arm. Then your resistance arm would be from the axis to the resistance. Okay, same concept. So in looking at these, it's important to note, so just right away, thinking about what we talked about with mechanical advantage, okay, looking at a first class, second class, and third class lever. In the case of a first class lever, okay, the mechanical advantage could go either way. You can have you could actually have it be at the point where you just have balance, where it zeroes out, okay? Or you could have a mechanical advantage of greater than 1 or a mechanical advantage of less than 1. What that's dependent upon when we're looking at a first class lever is where the axis goes. So if we were to move the axis this way, so say we were to put the axis right here, okay, what do you think that would do to the mechanical advantage? Would that make the mechanical advantage greater than 1 or less than 1? So it would actually make the mechanical advantage greater than 1, okay, because you increased the length of the force arm. Okay, if we took the axis and moved it this way, you would now have a mechanical advantage of less than 1 because you've shortened the force arm. You made the resistance arm longer. Okay, so again, it's the same thing as we talked about with that other picture. So the first picture you saw with the ball on the end was a first class lever, but the one you saw, it was a mechanical advantage of greater than 1 because of the fact that the force arm or the moment of the force was larger. Now, when we look at a second and a third class lever, okay, so in the case of each one of those levers, in one of them, the mechanical advantage is always greater than 1. In one of them, the mechanical advantage is always less than 1. Okay? So pair those up right now. Think about it for a little bit. Which one would always be greater than 1? Which one would always be less than 1? Okay, so if we look at the second class lever, pause it if you want a little bit more time to think about it because I'm going to give you the answer. So the second class lever, the mechanical advantage is always greater than 1. In the third class lever, the mechanical advantage is always less than 1. Now think about why that would be, okay? So if you got it right, good for you. If you didn't get it right, let's figure out what you're missing here, okay? The reason why the mechanical advantage of a second class lever is always greater than 1 is because the force arm is always going to be the longer of the two arms. Remember, it's a ratio of the force arm and the resistance arm. So in a second class lever, because of the way it's designed, the mechanical advantage will always be greater than 1. Okay, because if you look at this, regardless what you do with the resistance, say you move the resistance here to this point, the mechanical advantage, you don't have as much of a mechanical advantage, but you still have a mechanical advantage greater than 1. The reason being is that this force arm is still longer, okay? So if we moved our, I'll show you, it'd be a little easier if I draw it. So here, if we put the resistance arm here, okay? Now, here's the length of your resistance arm. Here's the length of your force arm. So you still have a mechanical advantage of greater than 1. Okay? So in a second class lever, that's what you're going to have. In a third class lever, the mechanical advantage is always less than 1 because your force arm is in between the resistance and the axis. So the force arm, again, you can move it, okay? So again, say we'll do the same thing here. Let's say we move the force arm from here to here. So now this is our new force arm. Okay? So there's our force. Well, the mechanical advantage is still going to be less than 1 because if you're in a third class lever, you're going to be having, there's still your resistance arm, there's your force arm. So your ratio is still going to be less than 1. Okay, so again, when you're looking at that, and again, I'm not going to be so much concerned about you like actually calculating numbers, but you should know that about these levers. Okay, so again, you have to look at that ratio. Okay, so it's the ratio of the moment arm through which the applied force acts to that through which the resistive force acts. If that force arm is bigger, you're going to have a ratio greater than 1. Now, with a first class lever, again, it could kind of go either way. So here's the reason why a first class lever, we sort of talked about it a little bit already. Let's just say that, again, I'll kind of show it this way. Let's do this. If we take, let's just say we shorten this. So say we cut, say this is just, again, we'll just pretend this is like a board on a little rotating axis, okay? We'll cut the board here, and we'll put our resistance here, okay? So what did that just do? So we don't have any of this over here. This is all gone, okay? So what did that just do? That actually increased the mechanical advantage because we have a longer force arm than a resistance arm. Okay, so it's still a first class lever. We've just changed the mechanical advantage. Okay, it's now the advantage is more to force production. Okay, so you actually get to apply less force to move this resistance. Okay. So that resistance now is easier for you to move. If we kept this like this, we push down to get that to go up, there's less force required. Okay? So again, step 1 in identifying what class of lever you're looking at, okay, is to look at your components. Look at where your axis is. The axis is probably the easiest thing to find. Look at your axis, look at where the force is taking place, look at the resistive force. Okay, look at that first. Once you see how all that lines up, you already know something about what the mechanical advantage is by looking at the distances. So first of all, if you know it's already a second class lever, you know that your mechanical advantage is greater than 1. Okay, if it's a third class lever, it's less than 1. If it's a first class, you do have to look at which arm is longer. Okay, and usually you can visually see that. So just make sure you could identify what it is you're looking at to be able to determine what class of lever it is, and then from there you get your mechanical advantage. So now what we want to do is we want to apply this concept to the body, okay? So we have muscles in the body that act through levers. That's going to kind of be our focus. We do have a lot of muscles in the body that don't function through levers, okay? So for instance, some of the muscles in the face, we have muscles in our arteries. They don't function through levers, but when we look at most of our movements, particularly in our appendicular skeleton, much of that is done through the use of levers. Again, it's not a different concept, it's just a different way of looking at it. So now we're just kind of applying that, you know, these pictures that sort of look like the seesaws or the teeter-totters in a playground, to just basically applying that to the body. Okay, so we have an advantage here. Now, sometimes there has to be some context when you're looking at how the muscles operate in the body as far as classifying them as levers. And this will be something that we explore more when we kind of meet face to face and talk about this, because this is a concept that could be a little difficult to understand. So I want you to kind of take your time with it and be able to see, so you're not, there doesn't have to be guesswork here. You can just look at something. As long as you can define those different parts, you can usually make sense as far as what it is that you're looking at with this. So if we look at this picture right now, so remember I said you have to find your force arm, okay, or your moment arm of the force, and you have to find your resistance arm. So we're looking at here is extension of the forearm against resistance. So you're just looking to extend your arm. So when we're looking at this is the tricep muscle right here. You have your elbow joint right here. So we're basically looking to extend. We're basically looking to take our arm and straighten it out. Okay. So we're going to have our force arm. So the force arm is going to, the force is obviously going to come from the muscle. So the force arm looks at where the tendon inserts at to the length of the muscle. You have your force or resistance. Okay, so that's where the force is going to be, right? So let's even make it easier. Pretend they're holding a weight. Okay, they have a weighted ball in their hand here. Okay, or they're holding a dumbbell. So they're holding a dumbbell in their hand and they're going to extend. Okay, so you look at the length of the resistance arm. Again, get your definitions down. Okay, so the distance, the perpendicular distance from the axis, which in this case would be elbow, to where the force is taking place. Okay, so this the entire, or the resistance is taking place. So here's your resistance arm. Okay, here's your force arm. Now when we measure this, okay, and again, you don't have to get yourself too wrapped up with this. So they're basically saying you have the length of your force arm is, they're measuring it here as 5 centimeters. The length of your resistance arm is 40 centimeters. So it actually gives you less. So even though it's a first class lever, okay, so again, remember with a first class lever, it could be that you have a mechanical advantage of greater than 1. You could have one that's less than 1, or you can actually have one where it is 1. And typically first class levers, when they're 1, they look to create balance. Okay, so you'll either have a lever that favors force, a lever that favors resistance, or one that favors balance with a first class lever. This one is at a disadvantage because the mechanical advantage is less than 1. Okay, because the distance of the length of the force arm is shorter. Okay, so what does this mean for this? Okay, so we have to apply more force in order to basically extend this weight. Okay, so we're actually at a disadvantage force-wise when we're looking at this. Now here's the thing with the body. So you're sitting there saying to yourself, well, geez, well, you know, our bodies are at a mechanical disadvantage. In many cases, that will be the case. However, in the case where the mechanical advantage is less than 1, it makes up with it by giving you more ability to move the resistance, meaning that you get greater movement. Okay? Now we have to apply much more force to create the movement, but you get the ability to move more. Okay, we'll talk about that more when we discuss third-class levers in the body and what that means, but that's essentially what you're looking at. You're looking at creating more movement with this type of situation. So here we look at a second-class lever, and really for the most part, it's pretty much agreed upon that this is actually the only example of a second-class lever in the body. So where you're getting, so here we're looking at the foot and lower leg, and what we're seeing here is that when you're weight bearing and you go up on your toes, that's really the only good example of a second-class lever. Okay, now again, let's look at this. So here's what we looked at in the previous slide with a second-class lever. This might help to make a little bit more sense of this. So here's your force, here's your resistance, here's your axis. Okay, so force, resistance, axis. Now, you kind of superimpose that here. Okay, so we have our axis. Okay, we have our resistance, which is kind of represented of basically our body weight. Okay, because again, that's what we're supporting here. And then you have your force here. So this and this are essentially the same thing. You have your axis, you have your resistance, you have your force. Okay, so this is the only example of movement in the body where the mechanical advantage becomes greater than 1. Think about why that would be important in this circumstance, okay? So for you to go up on your toes or be in a case when you're in weight bearing and plantar flexion, you have to support all of your body weight. So it's really important that you have a mechanical advantage greater than 1 in order to do that, because you're essentially supporting now all your body weight on this area, okay? Now, what you lose is movement, because if you think about moving from here to here, there's not a whole lot of displacement that occurs, okay? So while you gain force with a second-class lever, you lose the ability to create more displacement or movement, okay? So, because immediately, a lot of times when I ask the question, I didn't start with this, but many times I'll pose the question, well, what class of lever in our body is the most common? You know, I'll explain them, and students, you know, when I say, well, what do you think in our bodies? What do you think we primarily have? The immediate reaction is to say, well, second class, because we have to be able to move things and produce force. If that were the case, we would lose a lot of our movement, okay? We wouldn't be able to move as much. We wouldn't have the large ranges of motion in our body if we were all second-class levers. So yes, we would be able to produce a lot of force, but we wouldn't be able to move, okay? So our body, I'm kind of taking this away from the next section, our body is actually primarily comprised of third-class levers, okay? So this is a third-class lever here. So our body is primarily comprised of third-class levers for the most part. There are some first. Really, the only example of a second class is the weight-bearing plantar flexion, okay? So here's an example of a third-class lever. So again, if we go back to our seesaw representation, so here's our force, here's our resistance, here's the axis, okay? So it's a third. All right, so again, your mechanical advantage is always less than 1. So your force arm is here. This is where you're applying your force. Your resistance arm is here. So the mechanical advantage is always less than 1. Now let's look at the elbow flexion with the bicep. So the picture we're looking at here is of the biceps brachii. This is your elbow, okay? Here, I'll do this because it'll make it a little easier to again, if visually you're sort of looking at this. So I'll draw this here in the same way. So here's your axis, force. Remember, the force is in between the axis and the resistance when you're doing this, and here's your resistance. Okay, so this might be a little, this drawing over here will be easier for you to make the connection here because it's going in the same direction. So the axis, where's the axis? The elbow joint. Okay, your force. Okay, here's the bicep, there's your force arm. Same thing. The resistance, again, perpendicular distance from the axis to the resistance. So here you're looking at, again, your mechanical advantage is going to be less than 1. Now, again, you're sitting there saying, well, geez, our body's at a mechanical disadvantage. From the force production standpoint, that's true, but what you gain is movement. You have this big, large range of motion. If you take your elbow from full extension to full flexion, you have all of that movement that can take place. So while we lose a little bit of the ability to produce force, we gain motion. So in a class 3, in the case of a class 3 lever, while you lose force production, you gain movement. All right, and you can see that here. So I'll make another drawing. So let's just, again, this is kind of rough, but this is on the ground. So this is the ground. This is your little axis. So this is your teeter-totter again. We're going to put it all the way on the end because we're going to make it a third-class lever. Okay, so here's where you're applying your force. So we're going to apply the force this way because we want the resistance to go up, and here's your resistance on the end, your weight or what have you. So it'll take a lot more force to move this, but let's say you have the ability to movement. You can apply enough force to get this off the ground. Look at how much displacement's going to occur. So as this is moving, you're getting much larger displacement than you would with a second-class lever. If this were reversed in a second-class lever, yeah, you'd be able to provide a lot of force, but you wouldn't have as much movement. Okay, so that's why when we look at a lot of the joints in the body and the muscles and how they interact, many of them are third-class levers because, again, we have to be able to move. Now, we make ourselves stronger by, again, this is why we do, like, for instance, resistance exercise. We strengthen muscles through resistance so that they can get stronger and be able to overcome forces. Okay, whether that be through activities of daily living or for people who strength train for performance purposes, they look to gain that advantage. Okay, so we'll talk about some other advantages and mechanical advantages throughout the body. So really kind of look at that lever concept. It's one of the things that are sometimes a little difficult to see. We'll certainly spend some time face-to-face, or if you have questions about it, please, think of some questions, or what I sometimes tell students is look at other joints in the body and see if you can maybe apply based upon movement and whether you're weight bearing or not, what that actually means as far as the levers are concerned. So now we're just going to look at some other ways we kind of get mechanical advantages throughout the body. So our patella, okay, or our, as the layman term would be kneecap, but your patella is actually more than just a little bone that sits in front of your knee. What it actually does is it provides a mechanical advantage to the quadriceps muscle. Okay, so the patella increases mechanical advantage by kind of maintaining the tendon at a distance from the knee's axis of rotation. So we're looking here at the knee joint. Okay, so here's a knee with a patella, here's a knee without a patella. So what the patella actually does is it keeps the tendon away, allowing greater force to be produced. So if you didn't have a patella, that tendon would just sit flat right up against the femur and would sit closer to the knee joint. So your force being produced would be really close to the axis of rotation, whereas here, it actually helps to maintain that distance, okay? So if you didn't have a patella, the absence of it would cause the tendon to fall closer to the knee center of rotation. So what that would do is it would actually shorten your moment arm, okay? So the muscle force, so obviously we know the quadriceps tendon is going to pull this way, but by keeping that moment arm much longer, it's actually keeping the mechanical advantage better as it kind of moves throughout the range of motion. Okay, so that's another way we kind of see the concept of moment arms and mechanical advantage being applied to the body. All right, here's another way we kind of look at the concept of mechanical advantage and moment arm. Okay, so it still applies to levers, but here we're focused more on the moment arm and the ability to kind of produce force. So another way we kind of look at this is if we look at the elbow, so we're looking at the elbow joint. If you kind of look at the different positions of the elbow joint, okay, so if you look at all of these different pictures, okay, what do you notice as far as the distance from the tendon, the tendinous insertion of the bicep in its relationship to the elbow joint? As you look at this, okay, coming to this point, don't worry about these two pictures yet, okay? Going from here to gradually flexing the elbow, what do you notice? Okay, the moment arm, or the distance from the tendon line of action, gets bigger. So what does this mean? As you go from here to here, your ability to produce force and create movement actually increases. Okay, so here's your distance here, getting longer. There's where it's at its longest. So when you're at 90 degrees, okay, when the moment arm is shorter, there's less mechanical advantage. So when your elbow is at 90 degrees, you have a much greater mechanical advantage to produce force and movement here. Okay, now as you continue to flex the arm, what do you notice then again happens? Now then again, you notice that the elbow, okay, or that moment arm, as the elbow flexes, now starts to shorten again. So what that means is once you get past that point, now what you're looking at is, again, that mechanical advantage is starting to go back down. Okay, so what that means is that, you know, in the case here where you're looking at the elbow joint, okay, and the amount of weight that's getting moved, as the weight gets lifted, okay, the moment arm that it acts through and the resistive torque is going to change as the horizontal distance from the weight to the elbow changes. Okay, so if we look at this next slide, so as we look at this, okay, so again, it's the elbow and it's kind of going through the range of motion. Okay, as we move through the range of motion, now again, your focus has to be as far as the person's ability to produce force and movement. You have to look at where the tendon inserts to the axis of rotation. Okay, so here we already talked about this. When the elbow's at 90 degrees, that's where that moment arm is the longest. The reason why that's important when we're looking at just kind of the body and movement and the ability to provide force. So we already know that most of the skeletal muscles operate at a mechanical disadvantage, okay? Because the elbow is a you know, in the case of the elbow here, we're looking at a class 3 leveler, okay? So it's really important that during like sports and physical activities that the forces in the muscles and tendons are higher than those exerted on objects on the ground or with things we're trying to move. So essentially what we look at here, okay, so if we think about this, where is this weight going to seem the heaviest? Okay, so in all these different points, so here's a point here, point here, point here, point here, and a point here. Where technically is the weight or the resistance arm going to be the longest or essentially be the heaviest? 1, 2, 3, 4, or 5. Well, in the case, if we're looking at, again, the definition of what the resistance arm is, okay, it's going to be here because it's the perpendicular distance. So if we look down here, here's the perpendicular distance. Okay, so to move from here to here, okay, isn't going to be as difficult. So we don't need the moment arm of the tendon to be as long to go from here to here. Here, it's at its longest. So what do we need? We need this tendon to be as far away, and that all matches up. So when the resistance is at its longest, or the resistance arm, or the moment of the resistance is at its longest, so is our force moment arm. Okay? At 90 degrees is where the tendon's going to fall the farthest away from the joint, so it matches up with where when the resistance is the furthest. So again, as we continue to flex, what we notice is that resistance moment gets shorter, so the tendon doesn't have to be as far away from the joint. Okay? So the further the resistance moment or the resistance arm moves, so does the force moment or the force arm. Okay, so it all matches up. So the body kind of is able to, so even though it's at a mechanical disadvantage, it's able to kind of match up and go along with what goes on as we kind of move through the body. So that tendon's ability to move, to be further away from the axis of rotation, creates that better advantage. So looking at skeletal muscle structure, so again, there are some variations in tendon insertion. So we know generally, again, in everybody where these muscles insert at. However, based upon your body structure, there can be some slight variations as far as how far away the tendons are from the joints in individuals. So, your tendinous insertions are where the tendons are attached to the bone, and in some individuals, based upon their body structure, they could be inserted either farther or closer to the joint line in general than in other people. And what we have in a situation where, say, the tendon is inserted farther from the joint center, usually results in the ability to lift heavier weights. It allows you to apply more force. Now, what that does, though, is it results in a loss of speed. Results in a loss of speed in your ability to contract fast. So what this does is this arrangement reduces the muscle's force capability during faster movements. So if you just think about a lot of your different sports and athletic endeavors, when you kind of look at like body structures and things like that, that's what this is basically saying. So again, it's sometimes the saying that the sport picks the person doesn't pick the sport. If you kind of go by that theory, a lot of times people tend to have better success because they're matching kind of their body structure. And again, we're all a little genetically predisposed, as far as athletically based upon our body structure. So, if you take, I guess the best way to look at this would be if you looked at most power lifters, their tendinous insertions are probably farther away from their joint centers. And if you look at the way most of them are built, you can probably kind of come to that conclusion. And then what that does is it allows them to produce more force. Now, power lifters, obviously, just because they're so strong, they could be, explosive to a degree, but they don't per se have that kind of explosive ability, say, that like a basketball player would have. Okay, where now maybe the tendons are maybe a little closer to the joint, where they kind of get a little bit more speed. So that could kind of dictate some of your what you can be a little bit more successful with based upon your body type. So here's what we're kind of looking at with this. Okay, so in picture A here, you can see that the tendinous insertion is a little closer to the joint center, where here it's a little further away. So configuration B, what you're looking at right here over on this side, is that it has a larger moment arm and thus has a greater ability for torque for a given muscle for force. However, there's less rotation per unit of muscle contraction, therefore it's a little slower, okay? Whereas over here, the insertion's a little bit closer. However, if you're looking at the range of motion that gets accomplished per unit muscle contraction, you're getting more.
So what this is saying is you can get a faster contraction here, you could get a stronger contraction here. Okay, so again, if that's kind of the way their body's kind of structured and designed in general, you could be looking at maybe two individuals who are maybe successful at different sports. This individual will, if again, all things being equal, they're the same way at every joint, which likely they probably are, they're probably more successful in sports where force development or activities where force development is a little more advantageous, whereas over here, where speed is a little bit more advantageous, they might be more adept at some of the skills related to that individual activity. So now we're going to move on to looking at ways to just describe movement. So we kind of talked about the things, as far as levers and things of that nature, kind of addressing that aspect of movement. Now we're going to look at ways to just kind of describe movement. The most basic way of doing that is kind of looking at the anatomical planes of the body. So we're going to look at the anatomical planes, and we're also going to look at the axes, okay, and they correspond with one another. So this is how we're going to describe our movement. One thing I will tell you is, as you're looking at this, if you're not looking at it now, in your textbook, pages 26 and 27, they kind of break down some of these movements. So again, if even some of the movement terms you're unfamiliar with, that could certainly help you with that as I'm going through that, because I don't have those illustrations in this presentation. So when we're kind of just looking at this in general, if you kind of look at the individual in this picture, this individual is in an anatomical position. So in the anatomical position, you're standing, your arms are down at your sides, and your palms are facing forward. We then have the reference points for the anatomical planes. So we have the sagittal plane, which cuts the body into right and left halves. You have the frontal plane, which cuts the body into front and back. And you have the transverse plane, which cuts the body into upper and lower sections. Okay, now the key with this when we describe movements is that you always describe a movement as occurring through a plane and rotating around an axis. So first, all we're going to do is look at the planes. So when we look at the planes, movement goes through a plane. So let's look at what movements are going to occur through the sagittal plane. So for instance, if you're in the anatomical position and you flex your elbows, so you bend your elbows, that's movement through the sagittal plane. Okay, elbow flexion, shoulder flexion. Okay, bringing your arm straight up overhead. Hip flexion, knee flexion, hip extension, knee extension. Those are all movements that occur through the sagittal plane. If we look at the frontal plane cuts the body into front and back. The movement of shoulder abduction, moving your arm out to the side, away from your midline and going up over your head. Shoulder adduction, bringing your arm back in that straight line to your body. Hip abduction, hip adduction, okay? Those are movements that occur through the frontal plane. Okay, those are some examples. As I'm going through this, and when I'm done, go back and think of others, okay? The transverse plane is primarily a lot of your rotational movements, okay? So shoulder rotation, internal and external rotation. Trunk rotation is transverse plane. You rotate your trunk. Hip internal and external rotation. Those are movements that go through the plane, through the transverse plane, okay? So that's the starting point to this description. Why it's important that you at least know this is that next we're going to talk about a corresponding axis. The easiest part about this is when you have the planes and the axes, each plane has a corresponding axis. So once you know the plane, you know the axis, and vice versa. Okay, they both correspond with one another. So here's your axes. Again, movement occurs through a plane and around an axis. So you have your frontal plane, or your medial lateral, your sagittal plane, or the anterior posterior, and your longitudinal, your vertical. So, and I want you to know both names. Your book only uses the terms in regards to the axes as frontal, sagittal, and longitudinal. I'm having you learn both, and the reason why is that, in other classes, it'll make it a lot easier because you're probably going to run into this again. You may end up for the axes, you may end up learning the different terminology, so I want to make you familiar with each one of them. If you look at this picture, you could kind of see, you can tell, so here you have your planes, so your planes are kind of represented by the square rectangular shapes, again, kind of cutting the body as we described. The axes are represented by the dotted line, okay? And again, the axes run perpendicular to the planes, okay? So in other words, if you move through the sagittal plane, so think of a movement, so right now, I'll give you a little bit of time. Think of a movement that runs through the sagittal plane. Okay, so if you said shoulder flexion, if you said hip flexion, if you said knee flexion, if you said elbow extension, hip extension, knee extension, they all occur through the sagittal plane. They occur through the sagittal plane. They rotate around the frontal or medial lateral axis. So movement that occurs in the sagittal plane rotates around the frontal or the medial lateral axis. So it's also called the medial lateral axis because that's how it runs. Okay? If we go through a movement in the frontal plane, so shoulder abduction, hip abduction, both forms of adduction, okay? Wrist, ulnar, and radial deviation, okay? They all occur in the frontal plane. They occur in a frontal plane and rotate around the sagittal axis. So if you notice, the sagittal axis runs perpendicular to the frontal plane. So again, if this person were to abduct their shoulder, bring their arm straight up like this and around overhead, they would be moving through the frontal plane and their shoulder would be rotating around the sagittal or the anterior posterior axis. Your rotational movements, we said, occur through the transverse plane and they rotate around the longitudinal axis. So if this person were to rotate their trunk, okay, take their trunk and rotate it, they would be moving through the transverse plane. They'd be rotating around the vertical axis, okay? So if you know the plane, you know the axis, and vice versa, okay? They correspond with one another, okay? It gets a little difficult if you don't understand it and try to memorize it, because you'll say, well, if it moves through the frontal plane, it moves around the frontal axis. That's not how it works. Remember, the axis runs perpendicular to the plane, okay? So if you move in the frontal plane, you're moving around the sagittal or the anterior posterior axis. If you're moving through the sagittal plane, you're moving around the frontal or the medial lateral axis. And if you're moving through the transverse plane, you're rotating through the longitudinal vertical axis. So again, go back to those pages that I discussed earlier and make sure you have a good understanding. Look at those motions, and again, this will be something that we certainly bring up, and if people have questions about, we can bring it up when we address it during our session.